Ancient structures built thousands of years ago outlast our modern concrete. A Roman architect once wrote that buildings should be constructed to stand for ages, a hint of profound knowledge we have since misplaced. This is the forgotten material science hidden in ancient masonry. By the end of this, you will understand how these old secrets could solve our biggest construction and environmental problems today. We will uncover how Roman concrete repairs its own cracks and how Inca walls dance through earthquakes without falling. What forgotten wisdom from our ancestors are we only now beginning to rediscover? Picture a master mason along the Nile, his hands coated in fine dust. He was far more than a laborer moving stone. He was an early materials scientist, meticulously testing local limestone, observing how different binders set in the desert heat. To unlock the secret of these structures, we must shed our modern arrogance. We have to stop seeing ancient masonry as a primitive craft and start recognizing it for what it truly was: applied materials engineering on a monumental scale. These builders possessed a deep empirical wisdom, a knowledge earned through patient observation and experimentation that spanned generations. Archaeological chemists studying ancient sites describe them as open-air laboratories, where the results of century-long experiments are literally set in stone. This was not guesswork, it was a systematic understanding of material properties, durability, and how structures interact with their environment over vast stretches of time. They mastered core principles we are only now quantifying with advanced tools. They understood particle packing, how to mix mortars with a precise blend of coarse and fine particles, so they locked together into a dense, almost impermeable matrix. They managed thermal expansion, designing colossal stone blocks with such precision that they could shift and settle during earthquakes or temperature swings without fracturing. Look at the Pantheon in Rome, its vast concrete dome still the largest of its kind in the world after nearly 2,000 years. Modern concrete structures are often designed for lifespans of 100 years, maybe 2. The Pantheon mocks that timescale. How was this possible without electron microscopes or chemical formulas? The answer lies in a forgotten way of seeing the world, where local materials were not just used but deeply understood and manipulated. This foundational shift in perspective is the key that allows us to finally appreciate the breathtaking innovations waiting to be rediscovered. A crack forms in a Roman aqueduct, a tiny fracture under immense pressure. Yet, over time, this flaw does not spread. It begins to mend itself, a silent chemical repair that has baffled modern engineers for centuries. This is the first great material mystery, the secret of Roman concrete. At its heart was a reactive, almost living matrix born from a simple but brilliant combination. Builders mixed lime with a special volcanic ash known as pulvis puteolinus, sourced from the Pasquale region. This was no ordinary dirt, it was the key to a chemical revolution. When silica-rich volcanic ash met lime and water, it triggered a slow-moving chain reaction known as a pozzolanic reaction. This process created an incredibly durable and water-resistant binder, a glue stronger than the stones it held together. Modern materials scientists express sheer astonishment at this ancient innovation, describing it as a form of prehistoric nanotechnology we are only now learning to copy. The magic unfolds when a crack appears. Water seeps into the tiny fissure, but instead of causing damage, it activates unused lime clasts trapped within the concrete. This triggers a new chemical cascade, forming fresh crystals of calcium silicate hydrate. These crystals grow slowly and deliberately, filling the crack from the inside out. It is a built-in repair system, a material designed to heal its own wounds. Nowhere is this more evident than at the Roman harbor of Caesarea. Here, concrete structures have been submerged in the aggressive seawater of the Mediterranean for 2,000 years. While modern concrete would have crumbled to nothing in a matter of decades, these ancient piers and breakwaters have not just survived, they have actually grown stronger. The constant interaction with seawater has continually fueled the pozzolanic reactions, creating a material that defies time itself. Just imagine the implications for our own world. What if our bridges, our tunnels, our foundations could possess this same innate resilience? The mystery of Roman concrete reveals a profound shift in thinking, a paradigm where materials are not designed to merely resist their environment, but to adapt and evolve within it. Yet for all the chemical genius of Roman concrete, another civilization achieved a mechanical perfection that seems to defy the very limits of human hands. The granite blocks of the Great Pyramid were fitted together with seams thinner than a credit card. How could a society without iron tools manipulate one of the hardest stones on Earth with such breathtaking accuracy? This is not a story of brute force, but of a profound understanding of material science, where workers turned the properties of stone against itself. They understood granite not as a solid, impenetrable mass, but as a crystalline structure with inherent weaknesses to be expertly exploited. Geologists point to evidence of thermal shock, a method where fires were built on the stone surface and then rapidly cooled with water. The sudden, violent contraction would create a controlled fracture line, allowing massive blocks to be split from the bedrock with remarkable precision. This was not random cracking, it was a deliberate technique born from observing how granite reacts to extreme temperature change. The true secret, however, lies in the finishing work. Experimental archaeologists have demonstrated how a simple copper saw, when used with a slurry of water and quartz sand, becomes an incredibly effective cutting tool. Quartz is harder than copper and even harder than the feldspar in granite. As the copper blade moved back and forth, it dragged millions of these microscopic, sharp quartz particles across the granite surface. The copper itself was just a delivery system. The quartz sand did the actual cutting, grinding away the stone molecule by molecule. This abrasive science allowed them to achieve those impossibly smooth, flat surfaces that fit together so perfectly. A stunning time capsule of this entire process remains in an Aswan quarry, the unfinished obelisk. Still attached to the bedrock, this colossal stone is a frozen moment in time, covered in the unmistakable marks of these tools. You can see the channels carved by teams of workers using stone dolerite pounders, and the precise lines where copper saws with abrasive slurries were tested. The sophistication is staggering, suggesting a knowledge of stone fracture mechanics that, in its practical application, rivals some of our modern quarrying methods. The question this precision forces us to ask is not how they did it, but what else we have underestimated about their technological vision. Far to the north, on the windswept hills of Scotland, stand the remains of Iron Age forts with a secret sealed into their very stones. Their ramparts are not merely stacked rock, they have been transformed, melted and fused into a bizarre, glassy substance. This is the third great mystery, the phenomenon of the vitrified forts. How, and more puzzlingly why, would ancient builders subject their own defensive walls to heat so intense it could turn granite into ceramic? The temperatures required are staggering, well over 1,100 degrees Celsius. This is not the heat of a simple bonfire, it is the forge-like intensity needed to work iron. To achieve this across entire sections of a massive stone wall seems almost logistically impossible for the era. Archaeologists and fire specialists have debated this for generations. Was this a deliberate act of defense, a way to strengthen the walls by turning them into a single, solid monolith that would resist both weathering and battering rams? Or was it a catastrophic result of conflict, the aftermath of a siege where a victorious army burned the fortress so completely that the very stones flowed like lava? Some researchers even suggest a ritual purpose, a ceremonial firing to symbolically purify or eternally seal a significant place. The material transformation itself holds the first clues. The stones used in these forts, particularly granites rich in a mineral called feldspar, contain their own hidden chemistry. When heated, feldspar acts as a natural flux. In simple terms, it dramatically lowers the melting point of the surrounding stone, allowing the entire matrix to begin fusing at a temperature that would otherwise leave it unaffected. These builders, whether by accident or design, were leveraging the innate chemical properties of their local rock. The sheer fuel requirement is almost unimaginable. To sustain such heat across a long wall would have required a veritable mountain of timber, carefully stacked and maintained for days. This was not a haphazard blaze, it was a controlled, monumental undertaking. At a site like Tap O North, the scale of vitrification is breathtaking, covering vast sections of the hill fort's defenses. The glassy slag is not a thin surface coating, it runs deep, suggesting a sustained and managed inferno. This points to a sophisticated, albeit lost, understanding of pyrotechnology. It forces us to reconsider what these communities knew about geochemistry and high-temperature processes. The vitrified forts stand as silent, stubborn monuments to a forgotten science, challenging our timeline of technological progress and asking us what other ancient knowledge was lost to the cold northern winds. The mystery of ancient materials deepens with a surprising ingredient: a medieval mason stirring a pot of mortar and pouring in egg whites or fruit sap. These acts were not born of superstition, they were deliberate chemical experiments. Bioarchaeologists analyzing mortar samples with tools like mass spectrometers have uncovered a stunning truth: ancient builders across the world were masters of biopolymer integration. They were manipulating the very properties of their building materials by blending the mineral with the organic. They discovered that proteins from substances like animal blood could act as natural air entraining agents, creating microscopic bubbles that dramatically improved the mortar's workability and its resistance to freezing and thawing cycles. Sugars from fruit extracts or honey served as powerful retarders, slowing the setting time of lime mortars so workers could lay stones with greater precision on a large wall. Tannins from tree bark acted as natural water repellents, creating a shield against relentless rain. This was a global phenomenon. In China, builders developed a legendary mortar using sticky rice. The amylopectin in the rice created a dense, durable organic-inorganic composite that displayed incredible strength. In Mesoamerica, the sap of the fig tree, a complex latex, was mixed into plasters to enhance their cohesion and weather resistance. Even Roman concrete recipes sometimes included unusual additives like cheese or animal hair, tweaking the material's performance in ways we are only beginning to comprehend. The proof lies in structures like the 1,400-year-old Hagia Palace in Japan. Here, the sticky rice-lime mortar has not only survived centuries but has demonstrated a remarkable resilience to seismic activity. The organic network within the inorganic binder creates a material that can absorb and dissipate energy, allowing it to flex and move without catastrophic failure. This ancient wisdom of blending biological and geological resources presents a profound question for our modern world. In an age of synthetic chemicals and high-emission production, could these sustainable, bio-based recipes hold the key to greener, more resilient construction? The answer may lie not in a laboratory, but in the quiet, enduring legacy of a recipe that included a bowl of rice. The stone walls of the Inca seem to breathe with the mountain itself. At sites like Sacsayhuamon, colossal blocks of irregular limestone, some weighing over 100 tons, are assembled without a speck of mortar. Yet the seams between them are so impossibly tight that you cannot slip a piece of paper into the joint. This is not just stacking, it is a three-dimensional stone puzzle of breathtaking complexity, a system known as kinematic compatibility. The principle is one of brilliant foresight. Each stone was painstakingly shaped, its multiple contact surfaces carved to interlock perfectly with its neighbors. The goal was not to create a rigid, monolithic wall, but a flexible assembly. When the ground shakes, these stones can shift and slide against one another, absorbing and dissipating the energy of an earthquake. They move together, then settle back into place, a unified mass that dances with the tremors rather than fighting them. Structural engineers who study these walls express a kind of professional awe. A rigid, mortared wall tries to resist seismic forces directly, and if the force is great enough, it will crack and crumble. But an Inca wall, with its intricate, interlocking joints, behaves like a flexible chain mail. The energy travels through the connections, losing its destructive power as it moves. The joints themselves are a masterclass in design. They are slightly wider at the back than the front, creating a self-draining feature that prevents water from accumulating and freezing. They eliminate mortar, which is often the weakest point in a wall, the first thing to weather and fail. The process of achieving this fit was an immense undertaking. It likely involved the use of wooden templates and countless trial placements. Masons would have had to understand the center of gravity for each bizarrely shaped block, knowing precisely how it would settle and bear the load of the stones above it. The true test of this engineering is Ollantaytambo, a fortress and temple complex built in one of the most seismically active zones on the planet. For centuries, it has endured the violent upheavals of the Andes, while modern buildings around it have succumbed. The stones have shuffled and swayed, but the walls stand. What does this ancient, flexible approach teach our modern quest for seismic resilience? Perhaps our strongest buildings should not be rigid, but smart, designed to move in harmony with the forces of nature, just as the Incas learned to do. High above, the stone ribs of a Gothic cathedral are not merely holding position, they are actively growing stronger with every passing decade. This hidden strength comes from a conversation between the building and the very air it inhabits, a slow chemical dance centered on a humble but extraordinary material, lime mortar. The secret lies in a cycle as elegant as it is ancient, a perfect loop of transformation known as the lime cycle. It begins with limestone, quarried from the earth and heated in a kiln to an intense heat in a process called calcination. This burning drives off carbon dioxide, leaving behind a caustic, reactive powder known as quicklime. When water is added to this quicklime, it undergoes a violent exothermic slaking, transforming into a smooth, plastic lime putty. This putty was the mason's clay, a material that could be mixed with sand and water to form a workable mortar. But the true magic started once that mortar was placed between the stones. Exposed to the air, it began a centuries-long process of carbonation. The calcium hydroxide in the mortar slowly absorbed carbon dioxide from the atmosphere, reversing the original kiln process and transforming back into solid calcium carbonate crystals, effectively becoming artificial limestone. This was not a quick set, but a patient, continuous crystallization that locked the aggregate into a dense, durable matrix. Conservation scientists who care for these ancient structures point out that this slow set is the key to their longevity. Unlike modern cements that form a rigid, brittle lock, The crystalline structure of carbonated lime mortar retains a degree of micro-flexibility. It allows the masonry to breathe, to expand and contract with temperature shifts, and to accommodate subtle settlements without cracking. This critical difference is highlighted by the two main types of lime used historically. Non-hydraulic lime, made from pure limestone, sets exclusively through this slow absorption of carbon dioxide. Hydraulic lime, containing clay impurities, has an additional initial set when it reacts with water, but it still continues to strengthen over centuries through carbonation. The failure of modern restoration efforts provides a stark lesson. When well-meaning contractors repoint historic stonework with hard, impermeable Portland cement, they often seal in moisture and create a rigid shell around the original, flexible masonry. The structure can no longer move as it was designed to, leading to trapped moisture and concentrated stress that causes the historic stones themselves to spall and crack. In contrast, repairs using traditional lime mortars allow the building to function as a unified, breathing entity. The question this ancient science forces upon us is profound. In our relentless pursuit of speed and initial strength, have we abandoned a superior, self-healing, and truly sustainable binder? The slow, intelligent set of lime mortar is a lesson in long-term thinking, a reminder that some of the strongest bonds are not formed in a day, but over the quiet passage of centuries. The very stones of the Great Pyramid might not be what they seem. A radical theory suggests these colossal blocks were not carved from the earth, but poured into place like a modern concrete. This is the Geopolymer controversy, a debate that challenges our most fundamental understanding of ancient construction. Proponents of this idea, a small group of materials scientists, propose that the builders possessed a lost recipe for an artificial stone. They argue that crushed limestone was mixed with a high pH activator, likely derived from natron salt or plant ash, to create a slurry. This reactive soup, an aluminosilicate binder, could have been carried in buckets and poured into wooden molds, hardening into a synthetic rock that was, in many ways, superior to the natural material. The implications are staggering. It would mean the Egyptians were not just master quarrymen, but pioneer chemists, manipulating matter on a scale we barely comprehend. Evidence cited includes the uncanny homogeneity of many blocks, the occasional presence of what appear to be air bubbles trapped within the stone, and microscopic organic fibers that some researchers suggest could be remnants of the baskets used to transport the wet mix. Skeptics, however, point to the overwhelming geological evidence. They highlight the identified quarries where precise tool marks match the pyramid stones, and they argue that the chemical signatures can be explained by natural limestone variations and the effects of thousands of years of environmental exposure. The debate often centers on advanced chemical analysis, with each side interpreting the same data through a different lens. The presence of amorphous silica, a glass-like substance not typical of sedimentary rock, is a key battleground. For some, this is the smoking gun of a man-made geopolymer reaction. For others, it is a product of later geological processes or even the result of modern contamination. This controversy forces a profound question. If true, does this represent a technological peak so advanced that we mistook its products for simple carved stone? The quiet, imposing presence of the pyramids now holds a new layer of mystery, asking us to reconsider not just how they were built, but what they are actually made of. These vibrant surfaces were far more than simple decoration. They were the final, brilliant layer of a deeply sophisticated protection system. Architectural conservators working to preserve ancient sites describe these multi-layer finishes as a form of ancient armor for buildings, a complex skin engineered for both beauty and incredible longevity. The process began with a coarse, well-keyed base coat, often mixed with straw or hair for tensile strength, that gripped the underlying masonry. Upon this, artisans applied a series of progressively finer setting coats, each layer meticulously smoothed and allowed to cure. The final act was the application of a thin, intensely hard polished wash, a mix of the finest lime and marble dust, sometimes with milk or plant oils, that was burnished to a gleaming, water-resistant sheen. This was surface engineering at its most advanced, creating a barrier that shed rain, resisted dirt, and protected the softer materials beneath from the elements. The Mayan city of Palenque stands as a stunning testament to this lost art. Today, we see muted gray limestone, but sheltered crevices and protected fragments reveal the truth, traces of a once brilliant palette, crimson reds from iron oxides, deep blues from azurite, and vibrant yellows from ochre. These colors were not painted on in a single layer. They were often integrated into the final plaster wash itself, becoming part of the material's very fabric. The resulting surface was not just a coat of paint, it was a dense, polished, mineral-based composite that could withstand centuries of tropical sun and torrential rain. How did they achieve such durability without a single synthetic polymer? The answer lies in the patient chemical transformation of the lime itself. The act of burnishing did more than create a shine. It compressed the surface, forcing the calcium carbonate crystals to align into a denser, less porous matrix. This process, combined with the right organic additives, created a finish that was remarkably resistant to weathering. The loss of these gleaming surfaces from most ancient structures has left us with a distorted view of the past, one of stark, bare stone. We have forgotten that these buildings were once alive with color and light, their polished facades reflecting the sun. Rediscovering the material wisdom behind these architectural finishes does more than restore history's true colors. It points toward a future where our own buildings could be both breathtakingly beautiful and inherently durable, clad in a skin that is itself a work of material science. The dome of the Hagia Sophia is an architectural whisper, a seemingly impossible feat of gravity defiance. Its vast scale was made possible by a brilliant understanding of weight, not as an enemy to be conquered, but as a variable to be managed. Ancient builders mastered the art of density management, deliberately selecting porous volcanic stones like pumice and tuff to dramatically reduce the dead load of their grandest structures. They were not just stacking materials, they were engineering with air, using the innate properties of specific rocks to achieve spans that would otherwise have collapsed under their own mass. Structural engineers who analyzed the Hagia Sophia express profound respect for this optimization, noting how the builders created a perfect gradient of materials, balancing immense strength below with strategic lightness above. The secret lies in the unique properties of these volcanic stones. Pumice is essentially a froth of volcanic glass, filled with countless tiny, sealed air bubbles. This gives it an incredibly low density, allowing it to float on water, yet the closed cell structure provides enough compressive strength to contribute to the structural matrix without adding crushing weight. Tuff, a welded volcanic ash, is slightly denser but still remarkably light for its volume, offering excellent insulation and workability. This was a globally understood principle. The Minoans sourced pumice from the cataclysmic eruption of Thera, now Santorini. Builders of Romanesque churches along the Rhine River utilized local Rhenish tuff, carving it into blocks for towering walls that would not overburden the foundations. Roman engineers famously mixed light scoria, a vascular volcanic rock, into the concrete used for upper floors and vaults, understanding that the lower levels could bear the heavier loads. The ultimate case study is the Roman Pantheon. Its revolutionary dome is not a uniform mass of concrete. If you could take a core sample from its base to its apex, you would witness a deliberate and intelligent material transition. The thick foundation and lower walls use a heavy aggregate of travertine and brick. As the dome curves upward, the mix changes, incorporating progressively lighter materials like tuff and pumice at the very top. This careful grading of weight created a stable, coherent structure that has weathered 2 millennia. This ancient strategy of selective material use poses a critical question for our modern construction industry, which is responsible for a massive carbon footprint. Could we emulate this intelligent use of locally available, lightweight natural materials to build more efficiently? Instead of relying solely on energy-intensive steel and concrete, could we rediscover the art of building with the very air captured in stone, creating structures that are both monumental and mercifully light upon the earth? Deep within the concrete of a Roman bath complex, archaeologists uncovered something startling: thin bronze bars silently embedded in the stone. This was not a random inclusion. It was a deliberate act of engineering, a primitive form of the rebar that defines our modern skyline. Ancient builders, masters of compression, were intuitively grappling with a fundamental weakness: concrete's inability to withstand stretching forces, its lack of tensile strength. While their stone and concrete excelled under the immense weight of compression, they knew that bending or pulling could cause catastrophic failure. So they began to experiment, weaving metal into the very skeleton of their structures. Metallurgists studying these sites have found a fascinating array of solutions, from iron clamps dovetailed into marble blocks to lead-dipped iron bars set in volcanic concrete, and even bronze strips laid within archways. Each was an attempt to make the masonry work as one, to hold it together against the forces that sought to pull it apart. Yet these early engineers faced a brutal paradox. Iron, while strong, rusts. As it corrodes, it expands with tremendous force, a silent pressure that can splinter the very stone it was meant to secure. We see this tragic legacy in the shattered marble of many classical ruins, where iron clamps, now just a stain of rust, have literally burst their stone prisons. The solution for some projects was to use more noble, corrosion-resistant metals like bronze, a costly but far more durable choice. This experimentation took many forms. In Greece, metal clamps bound massive stone blocks, transferring loads and stabilizing walls against lateral shift. In Roman arches, metal rods sometimes acted as tension ties, countering the outward thrust of the vault. There is even evidence of metal fibers, chopped pieces of bronze or iron, being mixed directly into concrete to create a rudimentary composite material, enhancing its toughness. The ultimate expression of this bold experimentation may be the Basilica of Maxentius in Rome. Here, engineers integrated bronze reinforcement into the vast concrete vaults on a scale rarely attempted. It was a monumental gamble, a clear recognition that to span such immense spaces, the concrete needed an internal backbone, something to hold it together in tension. The limited and sometimes problematic use of metal reinforcement poses a profound question. Were these builders groping blindly in the dark, or did they possess a nascent, practical understanding of the composite material principle that now underpins our entire modern built environment? Their trials, their successes, and even their failures reveal a mind already reaching for the future, a mind that understood strength often comes not from a single material, but from the clever union of two. Beneath the steamy surface of a Roman bath, an invisible shield was at work. A complex matrix of hydraulic lime and pozzolana formed a render so watertight it could contain vast pools for centuries, a material science designed to conquer the relentless power of water. Hydroarchaeologists point to a simple but profound chemical truth. This was a cement that thrived in the very element that destroys its modern counterparts. The secret was a reaction that could set and harden even when completely submerged, a property known as hydraulicity. While ordinary lime mortar needs air to carbonate, hydraulic lime contains clay impurities that react with water to form stable, insoluble crystals, creating a permanent, waterproof seal. This was the backbone of Roman maritime ambition, allowing them to build harbors that withstood the sea's constant assault and aqueducts that channeled water for miles without significant loss. But their mastery extended beyond chemistry into the very arteries of their cities. The lead pipes of ancient Rome, often scorned for their toxicity, display a mechanical durability that is humbling. Experts note that sections of these pipes, buried for 2 millennia, frequently survive in better condition than the modern replacements laid beside them just decades ago. A protective layer of mineral deposits formed on the inside, shielding the metal from further corrosion, a natural passivation that speaks to a deep understanding of long-term material behavior. This was not an isolated genius. In Mesopotamia, builders used thick layers of bitumen, a natural tar, to line canals and seal the foundations of their ziggurats against groundwater. The Minoans at the Palace of Knossos engineered a sophisticated drainage system with precisely fitted terracotta pipes, all sealed with a waterproof plaster that kept their sprawling complex dry. And then there was Opus Signum, the Roman wonder mortar. By mixing lime with crushed brick and pottery, they created a material teeming with reactive silica. This compound would undergo a powerful pozzolanic reaction, resulting in a reddish, incredibly dense and impermeable concrete used to line cisterns, baths, and fish farms. The question this ancient water wisdom forces upon us is stark. In a modern world where aging water infrastructure loses billions of gallons to leaks every day, what have we forgotten? Our pipes are often designed for decades, while theirs were built for millennia. The true lesson is not in the specific materials, but in the philosophy, a commitment to creating a built environment that exists in harmony with water, not just a temporary barrier against it. A whisper on the stage of the ancient theatre at Epidaurus travels with perfect clarity to the spectator in the very last row, a distance of over 50 meters without a single watt of electrical power. This was not an accident of architecture, but a deliberate fusion of material science and sonic engineering. The builders of these spaces understood that sound is a physical wave, and they manipulated the very substance of their structures to guide it. They selected limestone for the seating not only for its durability, but for its specific acoustic impedance, a property that dictates how sound waves interact with a surface. The stepped rows of seats with their precise geometry and rough texture were not merely steps for spectators, they were a sophisticated acoustic filter. Acoustic physicists who study Epidaurus note that this corrugated surface effectively scatters and absorbs the low-frequency rumble of a moving crowd, while cleanly reflecting the higher frequencies of the human voice directly upwards. This material and geometric combination creates a phenomenon known as virtual pitch amplification, where the intelligibility of speech is dramatically enhanced. The stone itself, with its inherent porosity and internal damping characteristics, prevents the harsh, slapping echoes that would ruin a performance in a smoother, harder material. Beyond the stone, builders integrated resonant chambers. In some Roman theaters, strategic niches housed large ceramic vessels, acting as Helmholtz resonators tuned to specific frequencies. These pots would sympathetically vibrate, absorbing certain problematic sound waves and reinforcing others, effectively tuning the hall like a musical instrument. The entire structure was a single, coherent system for managing sound. Modern concert halls, often plagued by dead zones or muddy reverberation, struggle to achieve what these ancient builders accomplished with stone and geometry. The lesson of Epidaurus is one of holistic design, where the material is not a passive backdrop but an active participant in the experience. It challenges us to ask whether our own spaces could become more harmonious if we once again learn to listen to the quiet conversation between a wave and the wall it strikes. Scattered across the Diquis Delta of Costa Rica lie hundreds of stone spheres so perfectly round they defy simple explanation. These are the Los Bowlers, ranging from the size of a small melon to colossal orbs over 2 meters across and weighing more than 16 tons. Their surfaces are unnervingly smooth, their curves breathtakingly symmetrical. For decades, their existence has posed a stark question to archaeologists and stonemasons alike. How could a society without metal tools, presumed to have only stone hammers and chisels, achieve such geometric perfection in one of the most stubborn materials on Earth, a rock called granodiorite? The answer appears to lie not in a single miraculous tool, but in a profound, almost meditative understanding of material reduction. Expert analysis suggests a painstaking process beginning with the careful selection of a large boulder. Workers likely used harder stones to repeatedly peck and pound the surface, gradually fracturing away large flakes. This was followed by an even more demanding stage, grinding the form with abrasive sand and water, perhaps using a slab of the same granodiorite as a sanding tool. The final act of polishing might have involved a slurry of fine stone powder and water, applied with leather or cloth for untold hours to achieve that signature glassy finish. This was a technology of immense patience, a skill set passed down through generations where the goal was not speed, but an unwavering commitment to an ideal form. The material science of the rock itself is central to the mystery. Granodiorite is an igneous rock, incredibly hard and crystalline. The builders were not fighting this hardness, but using it to their advantage. The consistent crystalline structure allowed for a surprisingly uniform removal of material through abrasion. Every swing of a stone hammer, every circular grind with wet sand, was a controlled experiment in fracture mechanics, slowly convincing the stone to release its ideal spherical shape from within. This leads to the equally daunting logistical puzzle. Once carved, how were these multi-ton spheres moved through dense jungle and precisely positioned? Theories suggest they were transported on log rollers or atop wooden sledges, a monumental effort requiring coordinated community labor. Some spheres were found arranged in precise astronomical alignments or in groups near important structures, hinting at a deep cultural significance that is now lost to time. The Los Bowlers stand as a silent testament to a specialized, perhaps even lost, technology for processing hard stone. They symbolize a threshold of ancient capability that we are still struggling to measure. Their quiet, perfect forms challenge our modern arrogance, asking us if we have underestimated the power of persistent, observant hands to shape the very bones of the earth. The brilliant blues and golds that once adorned the Parthenon were far more than decoration. They were a sophisticated fusion of art and material engineering. Ancient builders integrated color directly into the very fabric of their structures, mixing mineral pigments into plasters and mortars to create a unified system of strength and beauty. This practice, a form of ancient chromotechnology, meant the color was not a superficial layer but an intrinsic part of the wall itself. Conservation scientists using spectroscopic analysis have decoded these complex recipes, discovering how master artisans produced legendary pigments like Egyptian blue. This was a synthetic compound created by heating a precise mixture of silica, copper, a calcium compound, and an alkali flux to an intense heat. The result was a stable, vibrant blue that was chemically bonded into the lime plaster. Similarly, the deep red of cinnabar, a mercury sulfide mineral, and the rich green of malachite were not simply painted on. their specific particle sizes and chemical natures interacted with the lime binder, influencing the final material's workability and its resistance to the elements. The famous Roman red floors, for instance, often derived their color from red ochre mixed directly into the mortar. This iron oxide pigment was not just a colorant, it acted as a durable filler, contributing to the surface's hardness. In Byzantine architecture, craftsmen sometimes incorporated finely crushed colored glass or tesserae into their mortars. This added a subtle, divine sparkle to the walls of sacred spaces, a literal embedded light that interacted with sun and candle flame. We now understand this world was a riot of color, a truth vividly revealed in digital reconstructions of classical statues. These figures, which we envision as pure white marble, were originally painted with lifelike tones, their garments a symphony of brilliant hues. The longevity of these finishes is a direct result of their chemical stability. These mineral-based pigments are incredibly light-fast, resisting the fading that plagues modern organic dyes. By bonding them into the crystalline matrix of a carbonating lime plaster, the ancients created a colored surface that could endure for centuries. This sophisticated use of color reveals a civilization that saw no division between structural integrity and vibrant expression, building a world that was not only monumental but magnificently alive. The brilliant blue of the Ishtar Gate was not painted on, it was grown from the very body of the brick itself through a masterful command of fire. This was the pinnacle of ancient pyrotechnology, a process where earth was not merely hardened, but fundamentally transformed in carefully controlled infernos. Kiln masters of antiquity were material alchemists, manipulating temperature, atmosphere, and firing time with an artist's touch to force clay to reveal its hidden potential. They understood that the journey from soft, wet mud to a ringing, durable ceramic was a chemical pilgrimage, a metamorphosis locked within the clay minerals themselves. Modern ceramic engineers express deep respect for the consistency these artisans achieved, producing thousands of nearly identical glazed bricks for monumental projects without a single digital thermometer or programmable controller. Their only instruments were their eyes, reading the color of the flames and the glow of the kiln, and their experience, knowing precisely when to starve the fire of oxygen or feed it more fuel to create the specific conditions needed. The magic begins with the clay. When subjected to heat, the microscopic platelets of clay minerals shed their water molecules and begin to fuse together. At even higher temperatures, certain minerals within the clay melt into a glassy or vitreous phase that flows between the remaining particles, locking them into a dense, waterproof matrix. The degree of this vitrification determined the final product's character. A low fire created terracotta, still porous and familiar. A sustained, high fire could produce a clinker-like brick, so vitrified and strong it was chosen for foundations in wet ground or for the linings of aqueducts. The true brilliance, however, was reserved for the surface, the glaze. These were not mere paints, but sophisticated chemical coatings designed to fuse with the clay body. An alkali glaze made from plant ashes and silica could produce a beautiful, durable glass. A lead-based glaze, used with great skill despite its dangers, offered an incredibly brilliant, clear finish that made underlying colors pop with stunning intensity. The ultimate case study of this industrial-scale ceramic mastery is China's terracotta army. Each of the thousands of soldiers, from general to foot soldier, was a monumental ceramic project. The artisans had to master the thermodynamics of firing such large, thick clay sculptures uniformly, ensuring the outer skin and the dense core cooled at the same rate to prevent cracking. This was not a handful of parts, it was a full-scale manufacturing operation that standardized pastes, managed colossal kilns, and solved the complex puzzle of large-scale ceramic engineering. The secrets locked within these ancient recipes are more than just formulas for color. They represent a holistic understanding of how to harness one of humanity's oldest tools, fire, to create a new, synthetic stone from the most humble of materials. In an age of disposable goods, their legacy asks us a profound question. What could we build today if we combined our modern knowledge with their deep, patient wisdom for creating objects meant to truly endure? That careful examination of a limestone outcrop was a form of silent science. Ancient quarrymen and builders did not simply see rock, they read it, understanding that a single cliff face contained layers with dramatically different personalities and purposes. Theirs was a profound empirical knowledge of geology, earned through generations of hands-on testing and observation. They knew that stone from one bed could crumble in the frost, while the layer just above it would stand unyielding for millennia. This was a mastery of material provenance, a selective harvesting based on an intimate understanding of local stone behavior. Geoarchaeologists, by tracing the specific sources of stone used in monuments, have uncovered not just sophisticated supply chains, but a deep, practical comprehension of the landscape. These builders considered factors invisible to the untrained eye. They understood bedding planes, the natural lines of weakness in sedimentary rock, and used them to their advantage to split massive blocks with surprising efficiency. They recognized how mineral composition influenced durability, selecting stones rich in quartz for their hardness, or avoiding those with pyrite that would rust and stain over time. Even fossil content was a clue, indicating the density and historical formation of the stone. This knowledge directly guided every engineering choice. A foundation required a dense, non-porous stone that could resist groundwater. A decorative column needed a fine-grained, homogeneous material that could be polished to a shine. A massive lintel bearing immense weight demanded a stone with high compressive strength and no hidden fractures. Consider the blue stones of Stonehenge, transported over a great distance. They were not chosen at random. These stones are a specific type of spotted dolerite, prized for its incredible toughness and ability to withstand the pounding of tools to create those iconic shapes. In the sun-baked quarries of Egypt, builders selected a soft, fine limestone for the intricate reliefs covering temple walls, a stone that welcomed the artist's chisel, while reserving harder granite for the eternal cores of pyramids and obelisks. The ultimate example of this selective genius is found in the Carrara marble quarries of Italy. Roman engineers did not mine the mountain indiscriminately. They became connoisseurs of the stone itself, identifying and following the purest, whitest veins of statuary marble, renowned for its translucency and lack of disruptive veining. This was a sustainable and intelligent use of natural resources, taking only what was best suited for the task from the earth's generous but varied offerings. It prompts a challenging question for our own era of bulk extraction. In a world where we often use one type of concrete for everything, what have we lost by no longer listening to the unique character of the materials we build with? The ground shakes, but the wall does not fall. In the world's most volatile landscapes, ancient builders did not fight the immense power of the earth, they learned to dance with it. This was dynamic load management, a principle where a structure's strength comes not from rigid resistance, but from its ability to absorb and redirect energy. Earthquake engineers who study these sites describe them as masterclasses in seismic resilience, centuries ahead of their time. They point to the brilliant simplicity of a trapezoidal doorway, a shape common in Inca architecture. Unlike a rectangular opening with vulnerable 90-degree corners, the sloping sides of a trapezoid naturally channel forces downward into the foundation, strengthening the entire wall. Similarly, inward-leaning walls create a stable, pyramidal form that resists toppling, a lesson in managing a building's center of gravity against lateral shaking. Perhaps the most ingenious system is found in the timber-laced masonry of Kashmir. Here, builders embedded horizontal wooden beams within the stonework, creating a flexible grid. During a tremor, these beams act as shock absorbers. They flex and slide, allowing the masonry to move as a cohesive, ductile unit rather than a brittle monolith. The material choices were equally deliberate. They often used smaller, irregular stones with rough, high-friction surfaces. When bound with a soft clay mortar, these walls gained a crucial advantage. The mortar itself was designed to be a sacrificial element. Under extreme stress, it would crush and crumble before the stones could fracture, allowing the blocks to shift and settle into a new, stable configuration without total collapse. This entire philosophy represents a profound understanding of material behavior under the most extreme conditions. The Inca capital of Cusco stands as the ultimate testament. For centuries, it has weathered violent Andean quakes that have flattened modern reinforced concrete buildings around it. Its stonework, assembled with a masterful interplay of friction, geometry, and flexible joints, has swayed and settled time and again. What if our own seismic codes looked beyond pure strength and embraced this ancient wisdom of intelligent flexibility? The survival of these cities challenges us to build not as an unyielding force against nature, but as a resilient partner, moving in harmony with the Earth's immense power. Deep within a sample of Roman concrete, an electron microscope reveals a hidden fortress. This is the crystalline architecture that grants ancient materials their timeless strength, a microscopic landscape of interlocking plates and dense gels that modern science is only beginning to decode. Materials scientists describe a sense of awe when they first saw the perfectly formed crystals of strettlingite thriving within 2,000-year-old marine concrete. These are not random formations, they are the deliberate, though unintentional, result of a recipe that encouraged a strong internal skeleton. The slow, hot mixing process the Romans used was crucial. It did not just create a uniform paste, it allowed these reinforcing crystals to nucleate and grow steadily throughout the entire matrix, weaving a resilient three-dimensional web that binds the material together from the inside out. This is microstructural engineering at its most profound, where the internal architecture dictates the macroscopic performance. Compare this to other ancient binders. Gypsum plaster sets into a forest of needle-like crystals, which interlock to create a hard but somewhat brittle finish. Traditional lime mortar carbonates into a mass of plate-like structures, which provide good compressive strength but can be vulnerable to water over the long term. But the Roman pozzolanic concrete, with its volcanic ash additive, forms something entirely different, a dense, interlocking gel of calcium silicate hydrate, reinforced with those incredibly durable strettlingite crystals. This composite microstructure is the true secret. The most compelling evidence comes from the concrete of Roman breakwaters, submerged for millennia. Core samples show that the material does not simply resist the seawater, it reacts with it. The salt water percolates through the matrix, slowly dissolving residual volcanic glass and triggering the formation of even more crystalline strengthening phases. The microstructure actually becomes more robust and more densely interlocked over the centuries, a self-optimizing system that we are only now learning to analyze. This poses a revolutionary question for our own time. What if we could move beyond designing materials that are strong on the day they are poured, and instead consciously engineer modern composites with these self-optimizing, growing microstructures? The key to unprecedented longevity, to structures that become stronger with age, may not lie in a chemistry lab's new polymer, but in the quiet, crystalline wisdom hidden within ancient stone. A Phoenician ship cuts through the Mediterranean waves, its hull laden with more than just trade goods. On board, a master builder carries the most valuable cargo of all, the intimate knowledge of turning limestone into a powerful binder. This was the silent, human network behind the ancient world's greatest constructions, a living web of technological diffusion where material science flowed along trade routes, through war, and across cultural boundaries. Historians of technology trace these movements like detectives following a faint trail. The Romans, for instance, did not invent concrete in a vacuum. Their revolutionary use of pulvis puteolinus likely built upon earlier experiments within the Hellenistic world, knowledge that was absorbed and then spectacularly refined through Roman engineering ambition. The mechanisms of transfer were as varied as the techniques themselves. Skilled artisans were often the spoils of war, forcibly relocated to serve new masters and in doing so, carrying their unique building methods to foreign lands. Trade ships transported not only finished luxuries but also specialized raw materials, like sacks of the specific volcanic ash that made Roman concrete possible, creating a demand that spread the recipe itself. And sometimes knowledge was codified in technical manuals, scrolls that were copied, translated, and passed from one center of learning to another, preserving complex formulas for future generations. We see this global exchange in the spread of fired brick technology. Originating in the ancient Near East, the craft of kiln-firing clay into durable, modular building blocks traveled slowly westward, eventually being adopted and adapted by the Romans who used it to build their sprawling cities. Yet sometimes brilliant minds arrived at the same conclusion an ocean apart. The development of lime plaster appears independently in both the Old World and the Americas, a stunning parallel of human ingenuity solving the same problem of creating a smooth, protective wall finish. The ultimate conduit for this exchange was the Silk Road. It was not merely a path for silk and spices, but a bustling highway for architectural ideas. Innovations in vaulting, dome construction, and even decorative stonework moved between east and west, blending and evolving with every mile. But this transmission was never a simple copy and paste. Local material availability constantly forced adaptation and innovation. A builder who learned to use pozzolana in Italy might arrive in a land without volcanoes. His genius lay in identifying a local material with similar properties, perhaps a certain type of fired clay or even crushed brick, to replicate the chemical reaction. This dynamic process of learning, adapting, and sometimes forgetting helps explain the puzzling rises and falls in ancient building technology. A peak of knowledge in one era could be scattered by conflict, disrupted trade, or simply the loss of a single guild of artisans, leaving later generations to stare at a colossal dome and wonder how their ancestors ever built such a thing. The story of ancient masonry is not just one of local genius, but of a conversation that spanned continents, a conversation whose most profound lessons were often written in the language of stone and mortar, only to be silenced by the passage of time. For the master builders of antiquity, stone was never just stone. It was a substance woven into the very fabric of their worldview, chosen as much for its soul as for its strength. This is the hidden dimension of ancient material science, where engineering was inseparable from cosmology, and every block laid was a statement of philosophical and spiritual belief. Historians of religion note that many cultures perceived the earth itself as a living entity, and the materials drawn from it were believed to pulse with spiritual energy or represent specific divine principles. The brilliant white marble of the Greek temples was not merely a durable choice. Its luminous quality, its ability to catch and reflect the Aegean sun, made it the physical embodiment of purity, light, and the celestial realm of the gods. To build with it was to construct a bridge to Mount Olympus itself. In Mughal India, the deep red hue of sandstone was deliberately selected for imperial forts and tombs. This color was not an aesthetic whim, it was a powerful symbol of sovereignty and life force, a visual declaration of imperial power meant to be seen for miles across the plains. Far across the world, Mesoamerican cultures revered jade above all other substances. Its toughness was secondary to its perceived essence. It was the stone of life, of water, of maize, and of the soul itself, far more valuable than gold. This deep symbolic materiality often demanded extraordinary sacrifice. It compelled societies to transport specific stones across impossible distances, even when perfectly suitable local alternatives were readily available. Why haul the iconic blue stones of Stonehenge over 200 miles from the Preseli Hills? The answer likely lies in their perceived sacred origin, a power believed to be inherent to that particular place and that particular rock. In ancient Egypt, the choice of black basalt for royal sarcophagi was profoundly layered. Its extreme durability served the practical need for an eternal vessel, but its color was a direct symbolic link to the black, fertile soil of the Nile floodplain, the Kemeter, the source of all life. It connected the journey of the departed with the cyclical rebirth of the land, merging the underworld with the promise of regeneration. This fusion of the practical and the spiritual created a rich, multi-layered logic for construction. One must wonder, did this symbolic drive, this quest for materials with the right essence, inadvertently lead these cultures to discover and commit to the most superior, long-lasting substances through a form of directed experimentation? Their search for stone with a divine spirit may have been the very thing that led them to stone with an eternal body. A Mayan artisan in a steamy jungle would not use the same mortar as a Roman engineer on a dry hillside. Each understood that a material's true test was not its initial strength, but its long-term conversation with the local world. This was environmental material science, a practice where every plaster and mortar recipe was a bespoke answer to a specific climatic challenge. Climate archaeologists mapping ancient sites see a clear pattern emerge. The chemical fingerprints of mortars shift dramatically from one ecological zone to another, perfectly calibrated to resist the dominant threats of their region. In damp environments, the enemy was persistent moisture. Roman builders in such areas often mixed in crushed brick and tile, a material known as coxiopsto. These porous ceramic fragments created a capillary network within the mortar, allowing trapped water to drain away and evaporate instead of sitting and causing damage. In colder northern climates, the destructive force was the freeze-thaw cycle. Water would seep into pores, freeze, and expand, cracking the matrix from within. Some Norse and later medieval builders appear to have added salts to their mixes, a daring gambit that lowered the freezing point of the pore water, preventing this internal pressure from building. Along coastlines, the pervasive threat was salt crystallization. Wind-driven sea spray would penetrate masonry, and as the water evaporated, it would leave behind crystals that grew with immense force, slowly prizing the material apart. Builders in these zones selected aggregates with a similar thermal expansion coefficient to the binder, ensuring the entire composite expanded and contracted as one unit, reducing micro-cracks where salts could gather. Compare the mortar in the arid tombs of Egypt, designed to be hard and stable in a world without rain, to the pliable, organic, rich mixes of Southeast Asian temples that needed to breathe through monsoon seasons. The ultimate case of this environmental foresight is the ancient city of Mohenjo-Daro in the Indus Valley. This metropolis faced annual, devastating floods. Its engineers responded not with defiance but with intelligent absorption. They manufactured their bricks not from simple sun-dried mud, but from a carefully controlled clay mix fired to a specific hardness, and then bound them with a mortar designed to be both strong and sacrificially porous. When the waters came, the entire city's fabric was engineered to survive the inundation and drain efficiently, a built-in resilience that allowed a civilization to thrive in a floodplain for centuries. This ancient principle of hyper-localized material design poses a critical question for our era of climate change. Instead of shipping one standard concrete mix across the globe, what if we rediscovered the art of creating building materials that are born from and built for their specific place on Earth? A deep, cylindrical hole drilled into a block of Aswan granite presents a puzzle that defies simple tools. The walls of this bore are perfectly smooth, with a consistent spiral groove that suggests a drill bit of immense hardness and stability, a feed rate that seems impossibly modern. Manufacturing engineers examining these artifacts, like the granite boxes in the Serapeum of Saqqara, note the precision is comparable to what a modern diamond-tipped core drill would achieve. The mystery deepens with the evidence of lathe turning on stone vessels from pre-dynastic Egypt, where the symmetry and fine detail indicate a technology for high-speed rotation and rigid tool posts, a setup we do not associate with that era. The conventional explanation of using copper drills with quartz sand abrasive falls short, as such a method would produce a rough, uneven surface and would struggle to maintain the perfect concentricity and depth seen in these objects. This forces a difficult question. Were these artisans in possession of lost abrasives, materials harder than quartz? Some researchers point to the possibility of corundum, the mineral that forms rubies and sapphires, or even diamond dust, which could have been carefully collected and used in a slurry to give a copper tool the cutting power it otherwise lacked. These substances occur naturally, and their selective use would explain the pristine finish on the hardest stones. Yet other theories venture into more speculative territory. Could a form of ultrasonic vibration, using a shaped tool and an abrasive slurry, have been employed to literally vibrate the stone away at a microscopic level? Or was there a knowledge of chemical dissolution, using plant-based acids to soften the stone surface for working, a method since forgotten? The case of metalworking is equally perplexing. Consider the Iron Pillar of Delhi, a massive wrought iron column that has resisted rust for over 16 centuries. Its composition and the skill required to forge such a large, pure iron object are marvels in themselves. But how were such hard metals cut and shaped with such precision? This leads to one of the most controversial artifacts, the Baghdad battery. This simple terracotta pot containing a copper cylinder and an iron rod could have been an ancient galvanic cell. If filled with an acidic electrolyte like vinegar or grape juice, it would have generated a small electrical current. While its true purpose remains hotly debated, some suggest it could have been used for electroplating, applying a thin layer of gold or silver onto metal objects through electrochemistry. The existence of such a device hints at a nascent understanding of electrical principles that, if applied to machining, could point toward a completely lost manufacturing paradigm. The evidence etched into the granite and metal of these objects is undeniable. It whispers of a sophistication we are only beginning to glimpse, a chapter in the story of human ingenuity that remains tantalizingly out of reach, challenging us to reconsider the very timeline of technological progress. The quiet chemistry of Roman concrete is now echoing in university laboratories worldwide. Modern materials scientists are not just admiring these ancient recipes, they are actively deconstructing them, molecule by molecule, in a race to solve one of our greatest environmental challenges. The production of Portland cement, the glue of modern concrete, is a colossal source of global carbon emissions. Researchers are asking a revolutionary question. What if the solution to this contemporary crisis has been resting in ancient ruins for 2,000 years? This new field, sometimes called paleo-inspired design, treats the ancient world as a vast library of proven, sustainable material solutions. A leading scientist at a major research institute recently stated that we are essentially trying to reverse engineer a technology that was lost to us because its performance in many ways still surpasses our own. The most direct line of inquiry involves self-healing concrete. Inspired by the lime clasts in Roman concrete that fill cracks, modern teams are developing systems where bacteria are encapsulated within the concrete mix. When water seeps into a new crack, it awakens these dormant microorganisms. The bacteria then consume a nutrient embedded nearby and produce limestone as a byproduct, effectively patching the fissure from the inside. Other groups are experimenting with tiny glass capsules filled with a healing polymer that ruptures and seals cracks upon formation. This is not science fiction. These are active, funded projects moving toward real-world application. Another powerful rediscovery is the value of fiber reinforcement. We see this echoed from the straw in Egyptian mud bricks to the animal hair in Roman plasters, a simple principle of adding tensile strength. Today, this manifests in engineered composites with synthetic or natural fibers like basalt or hemp, creating concrete that is far more resistant to cracking and impact. There is also a massive resurgence of interest in lime and geopolymer cements. These alternatives, much closer to ancient binders, require significantly less energy to produce and can potentially absorb carbon dioxide from the air over their lifetime, turning a building into a carbon sink. The most compelling modern application is a direct homage to Roman harbor concrete. Ambitious projects are now testing new concrete mixes that incorporate industrial byproducts like fly ash or even freshly quarried volcanic ash to recreate that powerful, long-lasting pozzolanic reaction. The goal is to build modern seawalls and marine infrastructure that, like their Roman predecessors, actually gain strength from decades of contact with seawater instead of crumbling away. The conversation between past and present is no longer theoretical. It is yielding tangible, promising innovations that could fundamentally reshape our built world, proving that the path to a sustainable future might just be paved with ancient wisdom. These ancient walls are more than monuments, they are irreplaceable libraries, and their books are written in stone and mortar. The unique material wisdom they hold is a non-renewable resource, a fragile record of human ingenuity that is actively fading from the world. When a section of ancient stucco erodes away, it does not just take a piece of history with it, it permanently deletes a chapter from this vast physical archive of science. This reality has given rise to a critical field known as heritage science, where chemists, engineers, and archaeologists work together to read these material books using the most delicate methods possible. Their guiding principle is to learn everything while harming nothing. They employ tools like portable X-ray fluorescence guns that can identify elemental compositions without taking a sample, and Raman spectrometers that use laser light to reveal the molecular fingerprints of ancient pigments and binders. Three-dimensional laser scanning creates perfect digital twins of entire structures, allowing for infinite study while the original remains untouched. These are the stethoscopes and MRI machines for ancient buildings, diagnosing their health and decoding their secrets from a respectful distance. Yet this scientific rescue mission is a race against powerful, accelerating threats. Air pollution deposits acidic compounds that slowly dissolve limestone facades. The increasing frequency of extreme weather events, from torrential rains to prolonged droughts, subjects ancient masonry to stresses it was never designed to bear. Perhaps the most heartbreaking damage often comes from well-intentioned but misguided restoration, where hard, impermeable modern cement is used to repoint soft, breathing historic stone. This cement acts like a rigid cast on a living body, trapping moisture and causing the original fabric to crack and spoil from within. At World Heritage sites like Pompeii and Angkor Wat, every conservation decision is now a profound ethical balancing act. Teams must carefully weigh the public's right to experience these wonders against the absolute necessity to preserve their physical integrity for future study. The work is painstaking, often involving micro-injections of compatible lime grouts to stabilize a wall, or the use of custom-designed shelters to protect fragile mosaics from sun and rain. The question we all face is not simply whether we can save these structures for their beauty, but whether we can preserve them for their knowledge. The ethical duty to safeguard our shared heritage is, in a very real sense, a scientific imperative for our own future. The solutions to our modern challenges in sustainable construction and material science may very well depend on the lessons we are still learning from the past, but only if we can keep those teachers from turning to dust. Our journey through these ancient walls reveals a world where builders were far more than laborers. They were sophisticated engineers and intuitive chemists. We have walked through the silent, self-mending miracle of Roman concrete and stood in awe before the earthquake-dancing stone puzzles of the Inca. We have seen how medieval artisans stirred organic chemistry into their mortars and how entire civilizations selected stone not just for its strength but for its very soul. The undeniable thread connecting all these discoveries is that these technologies were not primitive. They were simply different, optimized for longevity and harmony with the environment in ways our modern, speed-obsessed industry is only beginning to comprehend. This forces a humbling reflection. What other profound knowledge, what entire branches of practical science have we lost to the erosion of time? What brilliant solutions lie buried not in the earth, but in the forgotten pages of our own collective ingenuity? Let this exploration be a call to see the ancient world with fresh eyes. Do not view these structures as a museum of dead techniques, but as a living library, a repository of brilliant answers to problems we are still struggling to solve today. I would love to hear which of these ancient material mysteries captures your imagination the most. Was it the self-healing concrete, the perfectly spherical stones of Costa Rica, or the vitrified forts of Scotland? Share your thoughts in the comments below. If you found this rediscovery of our past enlightening, please consider subscribing for more journeys into the hidden secrets of history. The stones of the ancients are still speaking, holding lessons for a more resilient and sustainable future, if we are only willing to listen.